Okay, let's start with the 13.4, which is motion in space, velocity, and acceleration. Okay, so the velocity is going to actually be a vector, and it's the derivative of the position vector. And then the acceleration is the derivative of the velocity, or the second derivative of the position vector. Okay, so this right here is going to be pretty much like you expect it to be. And then the speed, that's going to be the magnitude of the velocity vector. Now, let's do a few homework exercises, and then we'll come back to this part here, the projectile motion. So number one, we're supposed to find the velocity, acceleration, and speed of a particle, and this is with this position function. Okay, so based on what I just said, what's the velocity?
-7 sine t.
Yes.
Plus 6 cosine t.
Okay, so this is the -7 sine t in the first component, and 6 cosine t in the second component. So go ahead and put those in with the vector notation. Okay, so that's just the just taking the derivative. Okay, then what's the acceleration?
-7 cosine t and -6 sine t.
Yeah, okay, so that's going to be the acceleration vector. So I'm putting those in. Okay, Webassign agrees. Now the speed, which is the magnitude of the velocity. So that's the magnitude of this vector, which is going to be, if you square that, you get 49 sine squared. And then this one's going to be 36 cosine squared t. We can put that in like that, or you could split this first one up into, what is it, 13 sine squared t plus, and then it would be 36 sine squared t plus 36 cosine squared t, which is going to be 36. So we could write it like that. And then for the second part, sketch the path of the particle and draw the velocity and acceleration vectors for t equals pi/3. Okay, so does anybody know what path this is going to be? What is this going to look like? What is it? What kind of a curve is this going to look like? I guess you have the answers on. I guess you can see the pictures on Webassign. But so, and it looks like an ellipse, right? So, but let me kind of show you how to get that ellipse. So the x component is 7 cosine t, and the y component is 6 sine t, right? So if you take x squared, you're going to get 49 cosine squared, right? So if you take x squared and divide by 49, then you're going to get cosine squared. And if you take y squared and divide by 36, then you're going to get sine squared. Okay, so that's going to be 1. And then, of course, this is the equation of ellipse. and it's going to go out 7 points from the origin on the left and the right, and 6 points up and down from the origin is going to be where, and it's going to be, so so if this is 7 and that's -7, then, and then this is 6 and -6, then it's going to be going like that, right? Something like that. And so we're supposed to draw the particle and velocity acceleration for the vectors t equals pi/3. So that means you're going to calculate what the velocity is. And pi/3 is this angle here. Now, if you have it like this, where the cosine is first and the sine is second, okay, and they're both positive, then points on the ellipse are going to correspond to the angle. So if you have t equals pi/3 on the parameter, then that's going to be at the angle pi/3. That's going to be the point that corresponds to the angle pi/3 that makes it up with the positive x-axis. If it's set up this way, if it leads off with sine, or if either of these is negative, then something else might happen. It might be a different kind of situation where angles don't correspond to these angles. Okay, but this is the way it is if it leads off with if it's cosine and then sine, cosine with the x and then sine with the y. Okay, so you're going to plug in pi/3 to the velocity vector. And let's see here. If you draw the angle pi/3, then it's a 1 to √3. Okay, so what is the sine of pi/3? Yeah, it's √3/2, right? So it's going to be -7 √3/2, and the cosine is 1/2, right? So that's going to be 6 divided by 2, or 3. Okay, and so the velocity vector is going to be, you can also tell that it's going to be tangent to the curve. Okay, the velocity vector is going to be tangent to the curve. That's another way you can tell. And then acceleration, that's going to be -7 cosine t, so that's going to be -7/2, and -6 sine t, and so negative, what is that, 6 times the √3/2, so that's going to be 3√3. And that's going to be pointing, that's actually going to be pointing this direction. Okay, so both negative, like that, and pointing towards the origin. And so it appears that the upper right is going to be the answer. Okay, so let's go on to the next problem, number 2. Find the velocity, acceleration, and speed of a particle with disposition function. So I guess this is really similar to the last one that we just did, except it's got 3 components. So what's the velocity?
It's just the differentiation of the function.
Yes. So we're going to take the derivative of that, which is going to be what?
1, 2t,
Yeah.
and 0.
1, 2t, and 0. Good. And then the acceleration will be the derivative of that. So that's just going to be
0, 2, and another 0.
yes. Thank you. Okay. So and then the speed is going to be the magnitude of the velocity, which will be square root of the sum of those squared. So 1 plus 4t squared. So I'm just squaring that 2t to get that. Okay, so let's plug those in, plug those answers in, and see what happens. Okay, and then we're supposed to, again, for the same one, we're supposed to sketch the path that this makes. And to sketch the path, so sketching the path of the particle. So we have this equation right here. You notice that the z is always 3. So that means that if we are, if this is the z-axis right here, and the y-axis here, and the x-axis is coming out this way, then everything is going to be in the plane here at z equals 3. Okay, that's what that 3 means. And then over here we have x is t and y is t squared. So if we plug in, so t is equal to x, so we plug in that t there, and we get y equals x squared. Okay, so that's going to be a parabola coming out right. That's in the. It's entirely in the. It's going to be in the plane z equals 3, entirely contained in there. So that parabola there. Okay, and then when we have t equals 1, then the position is going to be, so you plug a 1 in for t, and what position do you get? So making t equal to 1.
1,
1 plus
1, and another 1, and it's just 3.
3. So that's always going to be 3. So that puts us where that's 1 and that's 1. So it's going to put us up here somewhere on the parabola, right there, on that part of the parabola. And then, of course, the velocity vector is 1, 2, 0. Okay, so the velocity vector is also going to be the velocity vector is also going to be tangent to the curve at that point. So it's going to come off something like that. And then the acceleration vector is 0, 2, 0. So that's that acceleration vector is pointing straight this way. So parallel to the y-axis, pointing that way. So it looks like now I could have got the lengths wrong, I think. It looks like the upper right again. Yeah, upper right is the correct answer. And so I think they might have their lengths wrong because V of t is 1, 2, 0 and A of t is 0, 2, 0. So A should be a little bit, It should probably be a little bit longer, but we're not going to worry about that. Okay, let's move along to number 3. Find the velocity, acceleration, and speed of this particle. Okay, so what's the velocity vector?
-7 sine t, 2 and
Yes.
7 cosine t.
Yes. And then the acceleration vector?
-7 cosine t, 0, and -7 sine t.
Okay, and the speed?
The speed will be 49 square root 49 square 49 sine square t. Oh, we're just using the numbers. Oh.
Okay, 49 sine squared?
Sine squared t plus 4 plus 49 cosine squared t.
Great. And then this and this combine to give you just 49.
Oh,
So the square root of
53.
53. Okay.
Beautiful.
Hey, we're moving along pretty fast here. That's weird. I thought I chose harder problems, but I guess not. Maybe it was from last time that problem that looked kind of easy, but turned out to be really nasty. By the way, we were actually on the right track last time. We were doing the problem correctly, and I finished it off and posted the solution I posted it up on Canvas. Plus, there's also another link. If from the video, there's a link that goes to a different website, my OneDrive website, that has the solution posted in a PDF format. Or as in solution, I mean this document that I'm writing on. And so you got to go to the very end of it. Okay, so number 4, find the position vector of a particle that has the given acceleration and the specified initial velocity and position. So this one's a little bit different. So we're given the acceleration, and we're supposed to find the position. So if this is the acceleration right here, then what's the velocity going to be?
Do you integrate or?
Yes, you integrate. So
17 t squared over 2,
Squared divided by 2.
yes.
and then e to the t.
And e
Now
to
that could be plus some constant. We'll put C1. And then you said what's this one, e to the t?
Yeah.
And then this one?
Negative e to the power of negative t. That's constant.
So that's that one. Now, what you do here is you apply this. Okay, so v of 0 is actually just C1. And then this is going to be 1 plus C2. And this is going to be
Negative 1.
plus C3. And then this is 0, 0, K. So equating that one and that one, you get C1 is 0. And then equating these two, what's C2 going to be?
-1.
Yes. And then, oh, I made a mistake there. This should just be not a K. It should be just a 1, and then a 1K. Okay, and then equating that and that. Let's see, maybe we'll work it out. -1 plus C3 has to be 1. So that means that C3 is going to be
2.
2. Okay, so now let's plug in the constants that we just got. And our vector becomes 17 t squared over 2 plus 0. And then e to the t minus 1. And then negative e to the negative t plus 2. So we get that now. And now, let's go for the position vector. So this is velocity. So what's position going to be?
Integrate again.
Yeah, integrate again. So this will be 17
T to the
t
power
cubed
6.
over 6, right?
Yeah.
And then let's call it d1. So this would be the more constant. So we can say c1 again. I'll just do c1s again. c1, c2, c3. Or should, now we should probably should d1, d2, d3 because otherwise we're not being precise. We're breaking the tedious rules of math. Okay, so what is the integral of this one?
E to the power of t minus t plus a constant.
And yeah, plus d2. Okay, and then this one?
Positive e to the power of negative t plus 2t plus another constant.
Yes, great. So, and now we know that r of 0 is j plus k, which is going to be 0, 1, 1. Okay, so r of 0 is, here we have d1. And then this is going to be, when you plug a 0 in for t, this is going to be a 1.
Yeah.
Yeah, 1 plus d2. And then when you plug a 0 in here, you're going to get 1 plus d3. Whoa. All the constants are 0, right?
Yeah, 0.
0, 0, 0. One of people's favorite numbers. Okay, so it's the lazy mathematician's favorite number. Okay, so now plug all those zeros in. And you have 17 t cubed over 6, e to the t minus t, and e to the negative t plus 2t. Okay, good. Let's see if Webassign agrees with us that that's the correct answer.
Yep, we got it right.
Yes. Yeah, that's it right there. Okay. So that stuff wasn't too bad. The next one, the final problem, there's only one more problem. Okay. So that is projectiles. Like if you're throwing projectiles or firing projectiles through the air. And of course, it's ignoring air resistance. So if you kind of think about this last problem that we did, we started with acceleration and then we worked through all this stuff here. That's sort of what you do here with projectiles. Let me go back to the first page. The idea is that your force is mass times acceleration. So the force acting on the object is its mass times its acceleration. And so that means the acceleration is the force divided by mass, which is going to be gravity. Okay, so acceleration is just basically going to be the gravity. Okay, so acceleration is gravity, but that does not. So like if your object is going this way, the gravity does not act in a horizontal manner. It's only acting vertically. Okay, so it's only pulling the object down. It doesn't have any effect on the x. Okay, so if you, in other words, if you start with like a given x velocity, then that's just going to keep going in that direction until it hits the ground, assuming that way. Of course, air resistance and friction of the air will slow your object down, but we are just ignoring that. So this is essentially what you have, and so if you launch an object with initial speed v0, okay, so you're basically launching it with an initial speed v0, and the angle with the ground is alpha. That's this angle here, and the v0 is the speed. Then there's a x component and there's a y component. Okay, so if we start with the acceleration being this, then the velocity is going to be the integral, right? So you integrate this, and you're just going to get 0 because that's plus a constant, right? So you're going to get a constant. We'll call it C1. And then this is going to be negative GT plus C2. And then we know that V of 0, the initial velocity, so this is our speed right here, it's V0 in this direction. The y component, the x component, I'm sorry, is going to be x0. I'm sorry. It's going to be the speed times the cosine of alpha. And the y component is going to be the speed times sine alpha. Okay, so V of 0 is going to be C1, and then you put a 0 in here, you get C2. But that's also going to be this right here. Okay, so that's just like the problem we just did. And then C1's got to be that, C2's got to be that. So we plug it back into here, and again, and then we have the velocity being V0 cosine alpha, and then then you have this GT, and then the C2 is V0 sine alpha. Okay, and then you take another integral for the position, and you're integrating with respect to t. There's no t's here, so this is going to be V0 cosine alpha times t, plus possibly another constant. And then this is going to be, let's put this one first. So this is V0 sine alpha t. And then integrating this, you get minus g t squared over 2, plus possibly another constant. But if you're launching it off the ground, so like if you put a 0 in for t, you're going to get d1, d2. So if you're launching it from the origin, if you're launching this object from the origin where this is 0, 0, then those are just going to get wiped away. And so then you end up with just this part. So this is your x component, and this is your y component. Now, if you're launching it from a point off the ground, or not launching at the origin, in other words, then these are going to be different. Then these could be different. Okay, so maybe that's x0, y0. Okay, so then in that case, those are what your constants are going to be. So at any rate, you have something like this. This will be your initial x component. And this will be your initial y component right there. Okay, so and this is going to be your path of motion. Okay, now if you're launching it from the origin and you want to know how far the object's going to go, or you want to know how much time it's going to take before it lands. Okay, so basically for that one, you take, so for example, let's say we want to find this right here. When is the object? So it's gonna take a path, and then it's gonna come back down and land somewhere. And you're like, okay, where is that gonna land? And how far and what time? So the time would be you take this right here. And you'd set that equal to 0. And when you solve that, you're going to get 0, and you're also going to get this. You're also going to get that. So that's how long it's going to take. And then you could say, if we plug this value into here, then that's going to, into this t here, then that's going to give us the range. And if you take if you plug in half of that value, then at t/2, it's going to reach the maximum height. Okay, so the maximum height is this one. Time is this. Range is you just plug time into here in x value, and that's going to tell you how far it is down there. Okay. So yeah. So that's projectile motion and everything behind that. So let's go to the last question, number 5. A projectile is fired with an initial speed of 230 meters per second. That's going to be your V0. And then your angle of elevation is 60 degrees, so that's going to be your alpha. The projectile is fired from position 80 meters above the ground. So from the equation that we just came up with, our position vector is 230. Cosine is 60 degrees. times t. That's the x position. I'm plugging in 230 for V0. I'm plugging 6 degrees in for alpha, and then I've got t there. And then the y component is going to be 230 sine 60 times t minus gravity. Now, gravity is 9.8. So that means that gravity divided by 2 is 4.9. So there's, it's minus 4.9 t squared. Okay, and then it's 80 meters above the ground. So that's plus 80. Okay, so y0 is 80, and the x0 is 0. Okay, so that's just, so this right here, R of t, is just plugging into this bottom formula there. Okay, so that's going to be, this is a formula for the position vector. Okay, so we want to know what the range of the projectile is. So if this is a position vector, then how do you find the range? I'll let you guys think about that for a minute.
Isn't the range
you know already.
x distance?
Yes, it'll come from here by plugging in a specific value of t. Okay, but you have to get that value. How do you get that value of t?
Can you use the y equation?
Yes, so you take this right here.
Set it equal to 0?
Yes, exactly. Okay, so you're going to set this you're going to set that equal to 0. Okay, and that's going to, if you find what, that'll give you the t, the value of t, at what point this is going to, the projectile is going to hit the ground. Okay, it'll also give you, well, okay, so this is negative 4.9 t squared plus 230 sine 60 degrees t plus 80 equals 0. So you use the
Quadratic formula?
quadratic formula. So that's your A, that's your B, and that's your C. So it's negative B plus or minus the square root of B squared minus 4AC, but this, it is a minus right here already, so that's going to be plus 4 times A times C. So you see all over, okay, that's going to be all over 2A, so double this, which is going to be negative 9.8. Okay, so if you, so this is going to give you two values, and so if this is 80 degrees off the ground, if this is 80 feet off the ground, then your projectile is going to go up, and then it's going to come back down and land on the ground, right? Okay, and this is the distance what we're after. So the t's will actually correspond to this value and this value, as if the projectile were launched from the ground and pass this point at exactly this velocity and angle at that point. Okay, so the two t's are going to be those two values. So what you want to do is use both negatives. Use the minus one. Use that one. Okay, and if you use that one, you get approximately 41.079. Okay, so that's going to be the time. The time from when it's launched here or fired here to when it lands is going to be 41.079 seconds. Okay, so now what do we do?
Then you multiply that, put that in for your x coordinate.
Yes, so then you're going to put it into here. Okay. 230 cosine 60 degrees times 41.079. Okay, and that's going to give you 4720.51, which you're supposed so put in 4721 for the range. So round it up to 4721. Okay, let's see if that works. It worked for me. Anybody else get it? Of course.
Yep, got it.
Yeah.
Okay, great. So now the next one is to find the maximum height of the projectile, the maximum height. And for that one, you could actually use this formula here. This right here. Definitely use that. Because the way that this is calculated, is, let me show you why that works. So what that's going to calculate is if it were to launch right here and go up like that, then if you were to use that, the formula on the front page for the range, it would give you this value here if you were to use that formula for the range, because that's assuming that it starts at 0. So it's going to tell you when it gets back to the original height. Okay, but if you use the maximum formula from the front page, which is this, so that's going to be, in this case, it's 230 sine 60 degrees squared over 2 times g, so 2 times 9.8. Okay, so that's the formula from the front page. That's basically going to say if it takes that much time to get to here, then when it's at t over 2 on time, we're talking time here, not distance, not the x distance, then it's going to be at the maximum height. And so you're just plugging in a t over 2 into that. But then you got to add an 80 because that's 80, and then you have this extra piece there. Okay, so calculating that, I get about 2124. Wait, no. 2104. Okay, and then the last part, find the speed of impact. So for that one, it's probably best to calculate the velocity. Okay, so this, again, this is the position right here. So what's the velocity going to be?
Can you just drop the t's on that, on the first two? Just take the derivative of it.
Yes. So you drop the t's. And then this one is 9.8 t. And then the derivative of 80 is 0. So you just get that. And you want to know at impact, so that the time at impact is 41 something, so 41.0 .0479. Yeah, let's go with the speed already. So it's going to be the square root of that squared plus all of this squared, but with this value plugged in for the t. Okay, so all this part is squared. And I get approximately 233.284, which means if we round it to the nearest whole number, that's 233 meters per second.